The introduction provides a historical overview and theoretical framework for understanding crystalline and amorphous solids in material science and crystallography. It begins with the ancient appreciation of crystalline solid, particularly single crystal jewels, and traces the development of crystallography from Rene Howey's observation to modern theories by William Hughes Miller, Auguste Braves, Arthur Maurice Conflans, and William Henry Barlow. These theories established the foundation for geometrical crystallography, describing ideal crystal structures and the deviation found in real materials due to crystal defects and disorder. In addition, discuss the distinct differences between crystalline and amorphous solid, focusing on their atomic structures and the challenges of understanding amorphous materials. While crystalline solids have well-defined atomic arrangement, amorphous solids lack this long-range order, making their properties less predictable and harder to characterize. Also, the introduction emphasized the need for a new conceptual framework and precise terminology to better understand and describe amorphous materials. This framework is crucial for distinguishing amorphous solids from crystalline ones and advancing the scientific understanding of their unique properties. Overall, the introduction sets the stage for exploring the geometric and topological models of ideal amorphous solids, contrasting them with the well-established theories of crystalline structure in crystallography. It highlights the semantic and conceptual challenge in defining amorphousness and underscores the ongoing scientific inquiry into the nature and origins of amorphous solids. In this problem statement part, I got two, which is coordinate groups of amorphous solid and density fluctuations, transport of atoms, and solidification. For coordinate groups of amorphous solid, for the first one is amorphous materials encompass naturally occurring substances like obsidian and synthetic ones dating back to ancient civilizations. They fall into two main categories, which is inherently non-crystallizable equilibrium glasses and crystallizable metastable glasses. The former includes cross-linked polymers and atactic organic polymers, while the latter includes metallic glasses, some metal oxide, and certain polymers capable of crystallization through annealing. These materials exhibit common characteristics such as amorphous X-ray, scattering patterns, and a glass transition temperature. For the second one is further breakdown by chemistry includes metallic glasses, where recently developed these exhibit non-directional atomic bonding and heterogeneous composition. For the second one is inorganic glasses, structure with directional bonds forming 2D or 3D networks. They prevent crystallization by disrupting covalent bonding patterns. And next, organic glasses, divided into subclasses including cross-linked copolymer networks, atactic polymer glasses, and linear polymer glasses, each with distinct vitrification behaviors. For the last one is amorphous thin films. From bimolecular vapor deposition, these lack crystalline X-ray diffraction peaks and exhibit non-reversible structural rearrangements upon heating. This classification highlights the diversity and structural characteristics of amorphous materials across different chemical composition and synthesis methods. For density fluctuation, transport of atoms, and solidification, discuss the process of solidification from both a phenomenological and atomistic perspective, highlighting the transition from liquid to solid phases in material science. Here's a summary of its key points. For the number one is phenomenological view of solidification. Solidification is defined as the transformation of liquid into a solid, where the solid retains its shape for a significant duration. This transition primarily occurs through cooling, reducing the temperature of the liquid until it solidifies into either a polycrystalline or amorphous solid. For the second one, each cooling curve and phase transition. The cooling curve of a liquid undergoing solidification exhibits an exponential decay as heat is removed. As I attach the figure below, at the equilibrium melting temperature, the liquid begins to transform into a solid. Depending on the cooling path from ABC or ABD, the liquid can crystallize into polycrystals or remain amorphous. For the third one is atomistic mechanics of liquids. Atoms in a liquid exhibit close-range interaction governed by quantum states and many-body interaction. Density fluctuation in the liquid phase are stochastic and follow a Gaussian distribution impacting local density. You can see the figure below. Expected density fluctuation in liquid phase in red line, also shown in approximate density of icosahedral cluster in green line, and singular density of FCC crystalline solid in blue line. The average density of the liquid is chosen to be 5% less than that of the FCC solid. Next, nucleation and crystal growth. With sufficient number of nuclei growing per unit time to overcome the prevailing heat loss, the temperature of the system will increase spontaneously as indicated in figure 1 by the path BC. Below the equilibrium melting temperature, solid nuclei, or we call it as embryos, form due to fluctuation in atomic density. These nuclei grow by atomic attachment, adhering to crystallographic rules and minimizing surface energy, leading to the formation of a crystalline solid. And then formation of icosahedral clusters. It has been noted before that the maximum packing fraction of maximally random packed hard spheres is approximately 0.64, whereas packing fraction of FCC or HCP arrangement is 0.74. The difference is over 15%, in stark contrast to systems such as pure metals, gold, copper, nickel, in which the interatomic interactions are close to centrosymmetric. The liquid and solid densities at their melting points are very close. For example, pure copper at melting temperature has liquid density of 0.992 and solid density 8.352, a change of only 4.51%. But in other systems, it is much higher. For instance, for polyethylene, it is 21%. And to solve this problem, formation of icosahedral cluster were used where metallic liquids near freezing points often contain icosahedral cluster with higher local packing densities than the surrounding liquid. These clusters serve a precursors to crystallization or may persist as amorphous structures depending on condition. Diffusion rate within such a disordered clusters is rapid due to the high temperature and large number of defects. Addition to the classical vacancy atom exchange mechanism for diffusion, there are alpha and beta mechanism for atomic rearrangement. These involve relative movement of atom in tetrahedral arrangement, characteristic of icosahedral packing, which lead to configurational and or chemical composition change requiring little free volume as shown in figure. addition, theory of solidification through glass formation is continuing to develop. Glass formation occurs when conditions prevent the formation of other crystal nuclei. The process that approached by Gibbs de Marquio involves rapid cooling that inhibits crystallization, leading to a disordered atomic structure characteristic of glasses. Also considers thermodynamic equilibrium and the concept of configurational entropy to describe the transition to an amorphous state. For 7 point is free volume and structural arrangement. Speedy amended the Gibbs de Marquio argument by introducing an additional parameter for the glass, which described the dependence of the glass structure on its volume and enthalpy. In glasses, free volume refers to atomic spaces available for atomic movement, distinct from crystalline structures. Structural rearrangement and local stress conditions play crucial roles in determining the stability and properties of glassy materials. In the figure, for the left one, volume temperature phase diagram for a liquid glass system. For the right one is a schematic representation of the configurational phase space for glass. For the 8th point is complexity of glassy materials. The behavior of glassy materials is influenced by microscopic density fluctuation and inherent structural complexities. The formation and stability of glass depend on cooling rates, chemical composition, and atomic packing arrangement. And for the last point is challenges and theoretical development. Theoretical models like the Gibbs de Marquio theory and atomistic approaches continue to evolve in understanding glass formation and structural realization in amorphous solid. Experimental and simulation studies contribute to refining theories and exploring the diverse behavior of glassy materials. The aim of this article is to develop a comprehensive theoretical model for atomic structures. One of the primary objectives is to develop a comprehensive theoretical model that accurately describes the atomic structures of amorphous materials. This model should account for the inherent randomness and lack of long-range order in this material. For the second one is incorporate geometric and topological features. The model aims to integrate geometric and topological features that are unique to amorphous materials, distinguishing them from the regular periodic structures of crystalline solid. And then for the next aims is differentiate amorphous from crystalline solid. Another key objective is to create a clear distinction between amorphous and crystalline solid, moving away from the traditional view that sees amorphous materials as merely disordered crystalline structures. This differentiation is crucial for advancing the study and application of the amorphous materials. Next, improve understanding of material properties, predict physical and chemical properties. The objective is to improve the understanding and prediction of the physical and chemical properties of amorphous materials. This includes properties such as mechanical strength, thermal stability, and electrical conductivity, which are influenced by their irregular atomic structures. Enhance material characterization techniques. The goal is to develop and refine techniques for characterizing the atomic structure and properties of amorphous materials, facilitating more accurate and detailed analysis. In summary, the objective focuses on developing a comprehensive understanding and accurate characterization of amorphous materials, differentiating them from crystalline materials, improving an understanding on research methodologies. This objective aims to address the challenge and advance the field of amorphous material science. I have got three methodology in this article, which is for the first one is historical review. The document reviews the historical development of crystallography and compares it with the evolving understanding of amorphous materials. It highlights key figures and developments in crystallography that have shaped the current knowledge of atomic structures in solid. For the second one, each current approaches. The methodology includes an overview of modern approaches to studying amorphous materials, such as geometric packing models and molecular dynamics simulation. These methods are used to analyze and predict the atomic arrangements in amorphous materials. For the third one, each proposing a new model. The document proposes a new geometric and topological model for an ideal amorphous solid. This model aims to provide a more accurate and comprehensive understanding of the atomic structure of amorphous materials, distinct from the models used for the crystalline solid. The result and analysis present the findings from various approaches and methodologies employed to understand the structures and properties of amorphous materials. This section highlights key insights gained from the study and discusses the implication of this result for the broader field of material science. And I got for the result is complexity of amorphous structures, lack of long-range order, where the result confirmed the amorphous material lack the long-range atomic order found in crystalline solid. The atomic arrangements are irregular and do not conform to any repeating pattern, making them fundamentally different from crystals. And atomic scale irregularities, detailed analysis shows that at the atomic scale, amorphous material exhibit significant irregularities in atomic spacing and bonding angles. These irregularities contribute to their unique mechanical and physical property. For the second one is molecular dynamics simulation. Simulation of atomic motion. Molecular dynamics simulation provide insights into the atomic motion and structural dynamics of amorphous materials. These simulations show how atoms move and interact in the absence of long-range order, leading to unique thermal and mechanical behaviors. And then temperature dependence. The result demonstrates that the structure of amorphous material can change in temperature, affecting their mechanical properties. For example, increasing temperature can lead to increased atomic mobility and changes in density and hardness. For the third one is physical and chemical properties. Mechanical properties. The analysis reveals that amorphous materials often exhibit high mechanical strength and hardness due to their irregular atomic structures, which resist deformation. However, they may also be brittle because of the lack of slip planes that facilitate deformation in crystalline materials. For the thermal properties, the results show that amorphous materials generally have lower thermal conductivity compared to crystalline materials. This is attributed to the lack of well-defined lattice, which impedes the efficient transfer of heat. For the optical properties, amorphous materials are found to have distinct optical properties such as transparency and unique refractive indices, which are influenced by their disordered atomic structures. These properties make them useful in various optical applications, including lenses and optical fibers. What I got in analysis is two analyses, which is modeling, limitation, and advanced. Limitation of traditional models. The result indicate that traditional crystallographic models are inadequate for describing the atomic structures of amorphous materials. The lack of periodicity and the complex atomic interaction in amorphous material require new modeling approaches. Advancement in modeling techniques. The study highlight the importance of using advanced modeling techniques such as molecular dynamics simulation and geometric packing models to gain a better understanding of the atomic arrangement and properties of amorphous material. These techniques provide a more accurate representation of the disordered nature of these materials. For the second analysis I got is future research direction. Future exploration of atomic structures. The analysis suggests that further research is needed to explore the atomic structures of amorphous material in greater detail. These include investigating the effects of different composition and processing conditions on the atomic arrangement and properties of this material. Integration of experimental and theoretical studies. The study emphasized the need for integrating experimental and theoretical research to validate and refine models of amorphous materials. This approach will help in developing a more comprehensive understanding of these complex materials and their potential application. The result and analysis section provides a detailed examination of the unique atomic structures and properties of amorphous material. It highlights the limitation of traditional models and the advancement in modeling techniques and the implication for material design and future research. The findings underscore the importance of developing a distinct theoretical framework for understanding and utilizing the unique characteristics of amorphous material. For the first key point of conclusion that I've got is the development of new bulk metallic alloys in the last 20 years with extended supercooled liquid region with high thermal stability and superior mechanical properties has led to resurgence of research activity in this field, both experimental and theoretical. For the second key point is the field of amorphous materials. Natural and synthetic is extensive with widely varying chemistry and chemical bonding. Yet all of these materials display the same structural characteristic, of which the main ones are an amorphous halo in X-ray scattering, a glass transition temperature in thermal analysis, electric, optical, and mechanical isotropy. For the third one is a theoretical model of an ideal amorphous solid has been defined, paving the way for the development of a theory of amorphousness. Such as a theory will provide a basis for characterization of amorphousness of materials, a clear definition of amorphous structure on its own terms, a definition of imperfection and in the structure that are characteristic of real amorphous material. Next, the development and application of density functional theory has allowed simulation of amorphous structure to a higher level of reality as compared to molecular dynamics computation. For the fifth key point is there cannot a permanency of site identification in amorphous alloys because of the non-existence of a lattice and the ease with which mechanism alpha and beta can change cluster composition. Next, as yet there are no sensitive techniques to measure the intricate details the amorphous structure of materials. X-ray diffraction of crystalline solid gives sharp bright peaks capable of measuring interatomic distance and position to a high accuracy. X-ray scattering in amorphous solids does not give the same high-definition peaks, which at present limits the analysis. The same applies to colorimetric measurements. Other techniques may be capable of providing better resolution. For the seventh key point, a theoretical ideal amorphous solid provides the baseline reference for metallic glasses. By definition, it contains random packing and no imperfection. For the last one is imperfection in amorphous solid can increase or decrease average body density depending on the type and content of flaws present. I hope you enjoyed this video presentation from me and thank you for watching.